Well, this is Unit 1, the Chemical Equilibrium, Comprehensive and Detailed Revision Notes, Introduction to Chemical Equilibrium. You can always find our notes on examprepnotes.net. The chemical equilibrium is a fundamental concept in chemistry that plays a vital role in both industrial applications and natural processes. It's essential to understand what is the meaning of the dynamics of reversible reactions. A reversible reaction is a reaction which goes in both directions. It can form reactants from products, or it can change product reactants into products. So it can go in both directions. It occurs in a reversible chemical reaction. So not all reversible chemical reactions are in equilibrium. A reversible chemical reaction is the one that goes in both directions. That's correct. Sometimes the speed or the rate of the forward reaction, which is going from the left, from the reactants to the products, is faster than the one going the other way. So I have option number one. The case number one is when the forward that goes from left to right has a faster rate more than the backward reaction. Sometimes in the case number two, the forward traction is slower in the rate. So the backward has a faster rate than the backward has a faster rate than the forward traction. This is case number two. So I will write here that the forward has a slower rate than the backward. The case number three, when the rate of the forward reaction is equal to the rate of the backward reaction. This is what's known as equilibrium. So this is what's known as equilibrium. Not everything is considered equilibrium, only when the forward is equal to the backward in the rate. So definition, rate of the forward equal to the rate of the reverse action. This is meaning that although the reaction continues to occur in both directions, there is no change in the concentration of the reactants and products. So the concentration of reactant and concentration of product will stay constant. Take care, don't say equal. It's not equal, it's constant. But what are the characteristics of the equilibrium? The equilibrium has to be dynamic, which means that there is something done. The reactants keep forming products and the products keep forming reactants. There is no stop. So the forward and reverse action continue to occur and only the rates balance each other out, leading to no changes in concentration or any other changes in pressure or anything that can be seen. So I don't see any macroscopic changes. What are the macroscopic changes? The changes that can be seen or measured. Although I don't see no changes, I know that there are changes happening microscopically. What are the microscopic changes? Changes that I cannot see or detect. So yes, there are microscopic changes, but no macroscopic changes. This means that their equilibrium is dynamic. So on a molecular level, reactions continue to happen. Reactants form products and vice versa. This is why equilibrium is thermodynamic, unlike a static balance where everything stops. So if these two guys are playing on the seesaw and they are sitting and they are not just moving, so they are sitting and not moving, this is an equilibrium, but this equilibrium is static. They are not moving, not because they are balancing out, but they are not moving because they are just sitting. So this is static equilibrium, and our equilibrium that we are explaining is equilibrium in dynamic. So this means that at the end, you see that these two guys are not moving. This is static, but actually they are moving. But why you don't see any changes? Because the speed by which this one works is equal to the speed by which this one works. So my equilibrium is dynamic, not static. The concentration of reactants and products remains constant at equilibrium, but not necessarily equal. For example, a large equilibrium constant indicates that the concentration of a product is much greater than the concentration of reactant, but each one remains constant. So if you have 10 moles of these reactants and 7 moles of the products, whenever you break any of the reactants and change in the products, the number stays the same. So if you broke one from this and it becomes 9 moles, this one of these forms again one of the moles. So this one changes, becomes 7 because it decreased, so it decreased by 1, it becomes 6, but after it decreased by 1 come here and make it 7 again, while this one has decreased, but from here come and make it 10 again. So it stays as 10 and 7 at the end due to the changes that's continuously happening. So the concentration remains constant and not necessarily equal. The system has to be closed. For equilibrium to be achieved, the reaction must take place in a closed system, meaning no reactants or products can leave the container or the place where I'm making the reaction. This ensures the reversibility of the process, because if the product has left, so if the product has left from the system, then how is going the products to go and react to form, or decompose to form the reactants back? If you make a reaction in which the forward and backward reactions equal, then in this case there is no closed system, then it's not going to be called an equilibrium. If it's closed, it's going to be called equilibrium, but if it is opened, it will be called steady state. It will be called steady state. Examples for the equilibrium in a closed system is the carbonated beverage in a sealed bottle. So I have a bottle of any beverage, and when a bottle is sealed, the carbon dioxide gas is dissolved in the liquid, and this makes the equilibrium between the carbon dioxide in the gas phase and the carbon dioxide in the liquid. Since the system is closed, there is some gas here evaporating to here, and then some is condensing back and going to the solution again. The concentration of the carbon dioxide here inside the gas and here inside the liquid, inside the air above it and inside the liquid, is constant once the equilibrium is established. If you have a reactor and you are making ammonia, industrial production of ammonia, nitrogen gas reacts with hydrogen gas to form ammonia. This equilibrium achieved if the reactor is kept closed, so there is no nitrogen or hydrogen or ammonia can come out. Whatever nitrogen and hydrogen forms ammonia, and ammonia is broken down into nitrogen and hydrogen again. This balance allows a continuous production and decomposition of ammonia until the forward and reverse reactions are equal in the equilibrium again. What are examples for steady state in open system? I have an open system. I have a river with water flowing at one point and leaving at the other. The water level seems to me that it is constant, but this is not equilibrium because it's steady state. New water is continuously entering and leaving. The inflow here is balancing the outflow. So this is an open system, is considered as steady state, not as equilibrium. The human blood glucose level, so this is the blood, and the glucose level in human blood is maintained at a constant level due to the continuous input. Like any glucose from food or from liver, glycogen is broken down and then consumption again by cells or energy. This is not an equilibrium, this is a steady state because there is continuous flux, influx and outflux, coming inflow and outflow, coming in and going out. So this is steady state, not equilibrium. Anything that has an open system is steady state. Anything that has closed system is in equilibrium. So actually, to try to understand what's equilibrium, it's like a busy highway with vehicles traveling in opposite directions. One represents the forward direction and the other one is representing the reverse or the backward direction. When the number of cars traveling in both directions is equal, there is no visible change. So if you have 10 cars moving in this direction and 10 cars moving in this direction, you will feel that the number is the same. If one of the cars left from here and become 9 cars and move to the other direction, then one of the cars will move here and become in the other direction. So the number will be still fixed 10 and 10. It's not necessary to be equal. So you might have 20 cars here and 10 cars here. Again, if one of the cars moves from here to here, this becomes 9 and this becomes 21. But then again, one of the cars moves from here to here. So again, this one becomes 10 again, and this becomes 20 again. So number stays constant at 10 and 20. No change in the concentration. It's a constant concentration, not equal, but constant concentration in both directions.